Imagine if you could have an algorithm with efficiency. Unlimited efficiency, but no efficiency. You may ask, what did that even mean? But here's an example. If I ask you to write a piece of code to multiply two numbers, you may give an amateur answer like, just do x times y. Well, that may be sufficient for standard 32-bit and 64-bit integers, but if my two numbers had a lot of digits? Then your stupid answer would run in O of n squared. But what if I told you that you can make an algorithm that runs in O of n log n? All it requires some grit, a firm handshake, and a 1729-dimensional Fourier transform. That's an example of a galactic algorithm, an algorithm with optimal asymptotic performance, but one that's impractical in real-world applications. This isn't just because they're confusing, either. Their constant factors are simply unreasonably, unimaginably large, to the extent that they'd yield no advantage on any realistically sized asset. Galactic algorithms aren't always useless, however. For example, the authors of the aforementioned multiplication algorithm stated, "We are hopeful that with further refinements, the algorithm might become practical for numbers with merely billions or trillions of digits." Merely billions or trillions, they say. Putting that aside, these galactic algorithms are useful in a theoretical sense, as they can prove or disprove conjectured asymptotic bounds. For example, if somebody finds an O of n of 2 to the 100 solution for the Boolean satisfiability problem, even if nobody would ever use it, they'll solve the P versus NP Millennium Prize problem and win $1 million. That's your homework for today, by the way. So, what's an even cooler galactic algorithm? Matrix multiplication. The brute force naive approach has a time complexity of O of n cubed, so what do you think the theoretical best time complexity is? If you answered any of these, you're wrong, and also dumb. The real answer is O of n to the 2.371339, according to a paper from a little over a year ago that proved from the old bound of O of n to the 2.371552. Big difference, I know. Their 44-page paper is intense, to say the least. It relies on applying a so-called laser method to the Coppersmith-Winograd tensor, a mathematical object designed in past research specifically for matrix multiplication. Sometimes you can make galactic algorithms without even trying. What's the best algorithm to determine whether a positive integer is prime? Elliptic curve primality proving is extremely fast, yet nobody has proven that it works in polynomial time. The Miller-Rabin test is extremely fast, yet it's probabilistic, even if the probability of error can be bounded to less than 10 to the negative 100. There's even a deterministic version of the Miller-Rabin test, yet its correctness depends on the validity of the generalized Riemann hypothesis. Another quick way for you to make $1 million, by the way. So, what's left? The AKS primality test, a method that's galactic because, in principle, it beats out all of those other unproven or probabilistic methods, but in practice, it's never used. There are many more places where galactic algorithms arise. Minimum spanning tree construction, the traveling salesman problem, cryptographic breaking, etc. At this point, it may feel like these galactic algorithms are useless leftovers relegated to footnotes on Wikipedia pages. Like you someday. Yet, when researchers dedicate hundreds or thousands of hours to designing these useless, unwanted algorithms, new techniques or theoretical insights can arise. That's more you can say about dedicating hundreds or thousands of hours into Valorant. As a final note, consider Strasson's algorithm for matrix multiplication, an invention in the 1960s widely considered a galactic algorithm with a time complexity of O of n to the log 7. Log is base 2. Nowadays, it's not so useless. It can be a realistically superior option on matrices as small as 500 by 500 versus the default n-cubed method. You see, it's possible for a galactic algorithm to blossom into just another state-of-the-art algorithm. Just like it's possible for you to like and subscribe.